Hello friends, welcome to Electronic Circuit Hub. So today we will understand the steady state analysis of the boost converter. Okay, in the last video we have seen design and simulation of the boost converter by using LT-Spice. Okay, so in this video we will understand boost converter steady state analysis, right? Boost converter steady state analysis. We will understand what is the small ripple approximation for the boost converter. Okay, we will understand what is the Volt-Sec balance for the boost converter. We will understand what is the capacitor charge balance for the boost converter, and we will see how do we derive the transfer function for the boost converter, right? So we will be deriving the equation for the inductor Volt-Sec balance. We will be deriving the equation for the capacitor charge balance, and we will derive the equation for the transfer function of boost converter. We will understand what is the conversion ratio. Okay, what is the conversion ratio of the boost converter, what is the transfer function of the boost converter, what is the equation of the output voltage for the boost converter. Okay, so all these things we will learn and we will understand in the today's video, right? So let us understand the basic circuit diagram of boost converter, right? You can see this is the Vs, which is the supply voltage, or sometime it is called source voltage, and that is connected to inductor L. Okay, that is connected to inductor L. The current flowing through this inductor is IL over time period T, and the voltage across this inductor is VL over time period T, and the polarity for the voltage is plus here and the minus here. Here, here we have a switch connected here. Okay, in place of switch we can use a MOSFET. So let us assume for our steady state analysis, here is a switch. So this is the position A for switch and this is the position B for switch, right? Then we have a diode, and then we have a capacitor. Okay, capacitor C. Current flowing through this capacitor is ICT. Okay, you can see. Then we have a load resistance that is called RL, and the output voltage VOT, and the polarity for the output voltage is plus here and minus here. So hope you understand the circuit flow of the boost converter. Okay, here in the boost converter your inductor is directly connected to your source voltage, then after that we have a switch, then diode, and then capacitor, and then we have a load resistance, right? Now, yes, this circuit we will be using for our steady state realization. So you already know about this circuit. Now that let us assume that this switch is connected at position A, right? If SW at A. So this is the equivalent circuit for your boost converter when you switch at position A. Okay, so you can see your supply is connected to your inductor, then this goes to here, and then you have your capacitor and your load resistance is connected. Okay, the output voltage polarity is plus here minus here, the inductor voltage polarity is plus here and minus here. So this is the case when this switch is at position A. Now when your switch is at position B, SW at B position, so at for this case your supply voltage Vs is connected to a inductor. Okay, then we have a capacitor connected to this inductor, then we have a load resistance. You can see this is the load resistance. The polarity for the output voltage VO over a time period T is plus here and minus here. Polarity for the voltage across inductor is plus here and minus T. The current flowing through inductor is IL over a time period T, and voltage across inductor is VL over a time period T. So this is basically the equivalent circuit when your switch is at position A and when your switch is at position B. You can say if you use MOSFET here in place of the switch, if you use MOSFET when your MOSFET is turned on, that means it is connected to a position A, and when your MOSFET is turned off, it is connected to your position B, right? So this is basically a equivalent circuit for your, right, your boost converter. Now let us move ahead. Okay, now we will realize the circuit for switches at position A. We will find the voltage across inductor, we will find the current across the capacitor, right? So let us say the inductor voltage VLT, VL over a time period T equals to Vs. So whatever your supply voltage, whatever your source voltage is, the same voltage will appear at your inductor. Okay, so VLT equals to Vs. If you do a small ripple approximation for this inductor voltage, what would be your inductor voltage? If you apply a small ripple approximation, that means you neglect your ripple components and you only consider your DC component, right? You neglect your ripple component and you only consider your DC component. So for this case, VL equals to Vs. That means your inductor voltage is equal to your supply voltage, right? So now if you want to find out the capacitor current, okay, current across this capacitor, which is equals to ICT. ICT equals to minus VO over a time period T divided by RL. So your capacitor current is VO divided by RL. Why I have considered here minus? Because the flow of your current is in this direction. The arrow marked here. Okay, that's why your capacitor current is minus VO divided by RL. If you apply small ripple approximation, you can find the capacitor current IC equals to minus VO divided by RL. That means minus output voltage divided by your load resistance, and polarity marked here minus. Okay, because the current is flowing in opposite direction, and you assume that your output voltage is plus here and minus here. So this is inductor voltage and capacitor when your switch is at position A. That means let us say if your MOSFET is turned on. Now when your switch is at position B, that means your MOSFET is turned off. So what is inductor voltage? Okay, so now you can apply KVL in this loop here. Okay, in this loop here. So if you apply your KVL, the voltage across inductor VLT equal to minus Vs, that means supply voltage minus VOT minus Vs minus output voltage. So this is the voltage across inductor. So if you apply a small ripple approximation for this case, your inductor voltage VL equals to Vs minus VO, right? Vs minus VO. So this is the inductor voltage when your switch is at position B or MOSFET is turned off. Now if you want to find out the capacitor current when your switch is at position B, the capacitor current is given by IC over a time period T equals to ILT. That means your inductor current minus your your load current. And what is your load current? Your load current is minus VO divided by RL. Okay, so your capacitor current is given by, for this case, ICT equals to IL over a time period T minus VOT divided by RL. Okay, hope you understand how it comes. ICT, you if you apply Kirchhoff current law, that is KCL in the node here where my arrow is. So this current is entering here, this is going outwards, and this is also, if you want to find out ICT, this current, what will be your ICT? ICT equals to ILT, that means inductor current, minus VO divided by RL, that is output or load current, and minus polarity for this plus here and minus here marked. Okay, if you do small ripple approximation for your capacitor current, what would be your capacitor current? IC equals to I minus VO divided by RL, right? I minus VO divided by RL. So why I have considered in I here in place of ILT, I assume that your input current, let us say if your input current is I, that would be a very same or very closer to your inductor current ILT. So for small ripple approximation, I've considered ILT equals to I minus VO divided by RL. So now you have four equation, right? You have four equation. Then we have two equation for inductor voltage and two equation for capacitor current, right? Now let me show you inductor voltage waveform, right? Whatever equation we have got here, so we have got when switch is at position A, that means for time period dts, okay, on time period, your voltage across inductor VLT equals to somewhere your supply voltage Vs, and when your switch is off for the duty cycle of d prime time ts, your inductor voltage is Vs minus Vo. That means supply voltage minus output voltage. So this is the inductor voltage waveform. Hope you understand. Okay, inductor voltage for on time and inductor voltage for off time, right? So by using those equation, I've plotted graph here, right? Now this is graph for waveform for capacitor current waveform, right? So ICT during on time or for the time period of DTS, TS is a total time period and DTS D is on time period. Okay, so for time period dts, we have capacitor current minus VO divided by RL. We have already seen, and for time period d prime time ts, the capacitor current is I minus VO divided by RL. So hope you understand. Now we will apply the inductor volt second balance. Okay, inductor volt second balance we have already seen in the buck converter video. The the area under this curve equals to 0. Okay, the area under this curve equals to 0. That means if you apply your volt second balance for inductor, what would be your equation? Okay, we will be considering one switching cycle, that means start from dts plus d prime time ts. So there is a one switching cycle, that means one on time and then we have off time, right? So uh, if you apply volt second balance for inductor, so this vs multiply by ts dts plus vs minus vo multiply by d prime time ts. Okay, this is what I have written here. This comes area, the sum of the area under curve, that means this here and here. Okay, if you further solve this, if you take some common Vs, then you have d plus d prime times minus Vo into d prime times. Okay, if you further solve this, your V out equals to Vs divided by d prime time. This is very important formula. You need to remember, this is very important formula. The output voltage for buck converter is given by Vs divided by d prime time. That means off time. Okay. What is the d prime time? D prime time is 1 minus d. Okay, that is d prime times. So this is very interesting and very important formula. You need to remember, you need to know how we have derived this formula and how what is the use of this formula, right? Now if you want to find out the transfer function or transfer ratio or conversion ratio of your boost converter, right? So the transfer function or conversion ratio, let us say it is given by TF, or small x is given by the output divided by input voltage, V out divided by V in, that means V out divided by V is equals to 1 by D. Okay, from this equation 1 by D, 1 by D prime, and if you further solve this, equals to 1 divided by 1 minus D. So this is very important formula. This formula VO equals to output voltage of boost converter is given by Vs divided by D prime, and that conversion ratio or transfer ratio of boost converter is given by 1 divided by D prime. Okay. So you can alter your value of D and here value of D, and you can find what is the impact on your V output, V out voltage. If you want to further solve it, VO equals to Vs divided by 1 minus D. Now you can assume, let us say if you have 50% duty cycle, so Vs divided by 1 minus 0.5, that means let us say if you have 12 volt at Vs and your duty cycle is 50%, so 12 volt divided by 0.5, you will have 24 volt at output. Hope you understand the role of these two equations. VO divided by Vs, VO equals to Vs divided by D prime, and the conversion ratio X equals to 1 divided by 1 minus D. Okay. Now let us understand inductor DC current analysis. Okay, what is the role of inductor DC current? So we already know the capacitor charge balance. From the capacitor charge balance, this we have already seen. This waveform we have already seen. Now we will apply the capacitor charge balance for this waveform. So if you apply the capacitor charge balance, that means minus VO divided by RL into your time period, that is dTs, plus 1 minus VO divided by RL into D prime time Ts. If you further solve this, this will come minus VO divided by R, that RL into D plus D prime plus ID prime. If you further solve, the inductor DC current I is given by V naught divided by D prime times RL or R. This is load resistance. Okay. So inductor current I is given by V naught divided by D prime times RL. Okay. Since we know that V output voltage of boost converter is given by Vs divided by D prime time. Okay. So if you replace your VO here, you will have equation I equals to Vs divided by D prime square RL. Okay, D prime square RL. So this is basically a DC current equation for your inductor or inductor DC current, right? I equals to given by Vs divided by D prime time square into R, right? Now, if you want to do inductor current ripple magnitude analysis, that means inductor ripple current analysis. So you have this slope. The current across inductor is given by Vs divided by L for on time, that is D, dTs, and the current across inductor is given by Vs minus Vo divided by L for off time, right? D prime time ds. If you apply inductor current slope during subinterval A is given by this equation, dIL over a time period T divided by dt equals to VL over a time period T divided by L. That means Vs divided by L. This is what? Vs divided by L. For this is the inductor current slope for the time interval A, okay, during sub interval A. Now inductor current slope during sub interval B is given by DIL over a time period T divided by T equals to VL T divided by L, and you know that voltage across inductor is VO minus Vs divided by L. So for sub interval B, you have Vs minus Vo divided by L. Okay. So you already know that change in inductor current, the change in inductor current which is given by delta IL, delta IL is given by slope into subinterval, right? So change in change in inductor current to delta IL is given by the slope Vs over L, Vs over L into dTs. Okay. And if you want to find out what is the inductor ripple current, this is very interesting formula which which has come right now. Delta IL equal to Vs divided by 2L into dTs. Okay, so you have to choose the inductor value in a such a manner to get so that you can obtain your desired inductor ripple current. Okay, so choose your inductor very carefully, right? So by using this formula, delta IL equals to Vs divided by 2L into dTs, you can choose your inductor, right? Now we will understand capacitor ripple voltage magnitude analysis. That means what is the ripple voltage across the capacitor. So for subinterval A, the capacitor voltage slope during subinterval A is given by dVc over a time period t divided by dt equals to ICT over a time period t divided by C equals to minus VO divided by RLC. We already know what is the ICT value. ICT equals to minus VO divided by RL, and this is the C. So this is the voltage slope for subinterval A minus VO divided by RL into C. And now capacitor voltage slope during subinterval B is given by dVct over a time period T equals to ICT over a time period T divided by C, and this you have I divided by C minus VO divided by RL into C. So this ICT you have already calculated how will it come. So if you replace ICT by this I minus VO divided by RL, then you can get this. Okay. Now if you want to find out change in capacitor voltage, that is given by the delta V. You can see this graph. This is a plot between Vt over a time period t. If you want to find out change in capacitor voltage, which is given by delta V, that would come equals to slope into sub interval, and you have minus 2 delta V equals to VO minus VO divided by RL into C into dTs. Okay, so here you have to mark, right, minus here. So this minus get cancel, and you have delta V equals to minus VO divided by 2 RLC into dTs. Choose inductor value to get the required voltage waveform. So this is the ripple voltage across the capacitor delta V, which is given by VO divided by 2RL into C into dTs. So you have to choose the capacitor value to get the desired ripple voltage. Okay, so hope you understand the basics of a boost converter. What is the inductor volt second balance for the boost converter, what is the capacitor charge balance for the boost converter. Okay, and how will you derive the transfer function for the boost converter. Okay, so if you have any question, feel free to ask me in comment section. Thanks for watching this video.